In this video, I'm just going to do several integration problems. I've called the video integration tricks just because there are different things that we can do to get a problem, right, an integral into a format that we can find its antiderivative. Not every problem starts in a nice, easy antiderivative format. And so one of the challenging things throughout this class is always kind of recognizing what steps do I need to take. And so far, we have very few integration methods. In this video, we're just assuming knowledge of u-substitution. But we do have knowledge of how to factor, how to work with trig functions, how to divide things out, how we can multiply by conjugate. So we have all these algebraic rules that we know how to work with, and u-substitution. So part of the challenge is recognizing what can I do or what trick do I need to use. And so that's really what I want to work on here. So we're going to jump right into an example. And I want to look at the integral from 0 to pi over 4 of dx over sine squared x cotangent x. All right, so the first thing that I'm going to do is I'm going to look at this and say, well, I can't take the antiderivative of a sine squared. I meant this to be cotangent squared. Fix that if you would please. I can't take the antiderivative of sine squared cotangent squared, especially when it's in the denominator. I have no idea what that looks like. So one trick that we always find helpful with trig is to write things in terms of sine and cosine. Cotangent is cosine over sine. And so if it was squared, well then both of those have to be squared. And the second we do that, we recognize very quickly that the sine squareds cancel. We're left with dx over cosine squared x. So better, right? This is looking much better already, but this is still not something that we know how to find the antiderivative for. Cosine squared, even if it was in the numerator, we couldn't do that directly. We would have to use something else. But as it is, the cosine's in the denominator. So let's go ahead and at this point move it up to the numerator, because if we do that, we get secant squared x. And that is something that we can do the antiderivative for, because we know the derivative of tangent is equal to secant squared. So we have tangent x, and we're evaluating this from 0 to pi over 4. Now, other tricks that we might see with trig, always I think helpful to write things in terms of sine and cosine. That is very helpful. Reduce it as much as possible. It won't always be that we have a secant or cosecant squared. So what if we'd had sine or cosine? Well, we still can't work with those exponents if it's a sine squared or cosine squared, but we can use power reducing formulas. So we have to remember not only basic identities like the reciprocals, the quotients, we have all those formulas available to us as well. Power reducing, half angle, double angle. We have the Pythagorean identities. So trig, there really are a lot of different places that we can go with that. Just to finish out the problem, I'm going to plug in my pi over 4, and my 0, tangent of pi over 4 is 1, tangent of 0 is 0, so there's my answer. Let's take another example. Let's take the integral dx over x minus square root of x. So the last one was a definite integral. We had the limits on the integral. This one is an indefinite integral. That's fine. We're going to still have to calculate an antiderivative. We just know on this one we're going to have the plus c. So here I'm not seeing a ton that I can do right away because I just don't know how to work with this 1 over x minus square root of x. That is a more complex chain rule than what I'm prepared to work with. I could write this in the numerator if I wanted to, but it still is x minus square root of x to the negative 1 power. So let's take the complicated bit there, that square root portion, and let's do a little u substitution with that. Let's let u equal the square root of x, which means du is equal to 1/2 x to the negative 1/2. And then we have our dx, and so then if we want to solve for dx, dx would be equal to 2x to the 1/2 du. And I think I'm going to need it, so I'm going to go ahead and solve for x as well. X would be equal to u squared. So let's see what this does for us. Well, we can replace the dx with the 2x to the 1/2 power du. And on the denominator, we would have u minus, we would have x minus u. So we still have a lot of x's on the board. This was just a direct replacement, and so dx we replace with the du term, but it didn't quite work out to give us something without an x, and we still have that x in the denominator from before. All we've done is replace the u and the dx. So really we need to come back here and replace these as well. So remember, we called u the square root of x. So this 2 x to the 1/2 power, that is just 2u du. And then x, I can write that as u squared minus u. So what does this do for us? Well, let's think about factoring out that denominator. We can write this as u over u minus 1. And now we notice that the u's cancel. So we have the integral 2 over u minus 1 du. And now, because we only have that one u term, this is something that we should be comfortable taking the antiderivative for. Is a natural log of u minus 1. Of course, we need the plus the e. And it does need to be the absolute value of u minus 1. Remember, when we take the antiderivative of 1 over x, it is the natural log of x, of the absolute value of x. So at this point, we're almost done. We just need to replace that u with what u was, which is the square root of x. And there we have it. So the square root was a piece that was kind of throwing us there. We didn't recognize what to do with that, so we let it u-substitution stand in place of it just to get rid of those square roots, clean up the problem a little bit, and then it became a much easier problem to factor. Let's move on to another example. Let's take the integral from 0 to 2 of 4x squared plus 3 over 2x plus 1 dx. More complex interior function here. We don't know what the antiderivative of that would be. If we just purely had the numerator, we would be fine, or the denominator would be fine. Now, you might be kind of jumping to the assumption that, well, let's let u equal the more complex half of that, because we've done this a lot. We've done this trick where we say, if we have a fraction, let's let u represent one side of that. And we can try it, but very quickly we're going to see there's not going to be a way for me to simplify this much more, right? I can replace the numerator with my u. I can solve this for dx. Dx would be equal to du over 8x. But that's not going to help me a whole lot here. I'm not going to be able to simplify that 2x plus 1. Even if I were to solve this for x, I'd have some sort of messy square root. That's not going to clean up very, very quickly. So by all means, try to work it out further, but you're just going to see that it doesn't clean up very nicely. So let's think about what else we could do. Well, probably even easier than trying this u-substitution, trying to figure out a way to try and make it work, which is not, would be to recognize the numerator is bigger than the denominator, which means we can divide. We can take 2x plus 1, we can divide it into the 4x squared plus 3. And I'm going to use long division. We need to use long division because it's not a linear divisor. It is a linear divisor, I should say that. It's not a coefficient of 1 on the x of the divisor. So if I take my 4x squared and divide it by 2x, that would be a 2x as well. 4x squared. And then we have 2x times 1, which would be 2x. Now I'm going to subtract, so we have a negative 2x. The 3 comes straight down. And does 2x plus 1 go into negative 2x minus 3? Yeah, it does minus 1 time. And so we'd have a negative 2x minus 1. We'd subtract and we'd have a 4 left over. That is a remainder of 4. So remember, we can write that as 4 over the divisor of 2x plus 1. So what we can do is we can now write this integral from 0 to 2 as the divided out 2x minus 1 plus a remainder of 4 over 2x plus 1 dx. Now these have all become very easy to take antiderivatives of. The antiderivative of 2x is simply x squared. The antiderivative of negative 1 is x, and then the antiderivative of the fraction here would be 4, natural log of the absolute value of 2x plus 1. And we're going to evaluate this from 0 to 2. So always look to see, is the numerator of your fraction higher order than the denominator? If it is, there's a good chance we can divide, and it will help us immensely. So we'll have 2 squared minus 2 plus 4 times the natural log of 2 times 2 plus 1 minus, have 0 squared minus 0 plus 4 times the natural log of 2 times 0 plus 1. And so simplifying, we get 4 minus 2 plus 4 natural log of 5 minus 0, 0, then natural log of 1 is 0, and so that all just zeroes out. And so we can clean that up a little bit, 2 plus 4 natural log of 5. And that would be our answer. Again, we had a definite integral there, so we have no plus c. Let's take a look at this problem. Let's take the integral of d theta over the square root of 2 theta minus theta squared. All right, so if we look at this, we again don't know how to directly take the antiderivative because the inside of that square root is quite complex. But if we think about all the times that we see square roots in the denominator, right? There's nothing that we can really clean this up with. If we think about the times that we see the square root in the denominator, those stem from the derivative of the inverse trig functions if we had some perfect squares in there. So let's see if we can get a perfect square under that square root. So I'm going to have to complete the square. So the first thing I'm going to do is I'm going to factor out a negative just to make my life a little bit easier. Give me a negative 2 theta, which means I'm going to have half of negative 2, which is negative 1, and then I'm going to square it, and then still under the square root because I have to cancel out those terms under the square root. I don't have another side I can move it to. What we've just done here is we've added a 1, but not really a negative 1 because it was inside those parentheses. It is a negative 1, so I'm going to subtract a 1 right here as well. So now we can write this as d theta over the square root of, that should have been a plus 1. Let me take that back because we did create a negative 1. To balance out that negative 1, we would have to add the 1 to get it to be a 0. We are not adding on both sides, so we shouldn't do the same thing. We should do the opposite. That is a positive 1 times the negative is a negative 1. So to get it to cancel out, we need that plus 1 there. So now we can write this as a perfect squared, theta minus 1 squared plus 1. And just to completely rewrite it in a format that we're more comfortable seeing, d theta over square root of 1 minus theta minus 1 squared. And this is now something that we should recognize as the derivative of the inverse sine function. 1 over the square root of 1 minus. Our x is just a little bit more complex. Now if we wanted to let that x do a little u-substitution with this x right here, we could, but because the derivative of that inner function is just 1, it doesn't matter. So the antiderivative of this thing will be the inverse sine of theta minus 1. Then because it is indefinite integral, we need that plus c. So we do want to be on the lookout for our inverse trig functions. We have those square roots in the denominator. There is a chance we could get to it using the inverse sine or the inverse cosine function. If we have a square root with an absolute value, think about your secant and your cosecant functions. Let's do just one more. This one will be a nice quick one. Let's take the integral from negative 1 to 1 of the square root of 1 plus x squared sine x dx. We'll look at this for a few minutes, and maybe we'd want to try and use u-substitution, but I don't think that's going to work because I'm never going to get a 1 plus x squared or derivative of that to cancel with the sine, so that doesn't seem like it's going to work at all. I can't distribute that sine into it anyway. There's no way for me to find a perfect square and somehow get to simplify with a sine, so I'm really not seeing a whole lot I can do here. But let's think about the bigger picture. And I should note, eventually we'll have other integration techniques to throw in with this as well, but let's think about a way to view it the simplest way possible. We have a definite integral here. We're going from negative 1 to 1. Let's think about this function. Square root of 1 plus x squared, that would be an even function. And then sine x is an odd function. So because we're combining them through multiplication, because if we're to plug in that negative x here, it doesn't change, and this one were to change, that does make the function as a whole an odd function. Well, if we have an odd function, then it's balanced around the x is equal to 0. We're going from -1 to 1 here. Remember, we had a theorem that just simply says the integral of this is 0. Because we have an odd function, and because our limits are evenly balanced around 0, we get just 0. And that's the fastest way to do this problem. So it is always helpful to be on the lookout for odd and even functions. Even functions don't get us to just 0, but we can shorten up the interval a lot. We can say, let's just go from 0 to the number. But odd functions can get us to the answer very, very quickly. So keep all of these ideas in the back of your mind. Of course, there are other tricks that we can use as well, but hopefully this gives you a good idea of some of the things that we can do. We always want to be on the lookout for simplification, whether it be through division or factoring or just simply adding, subtracting. We want to be on the lookout for, can I use u-substitution in an effective way? Can we in some way manipulate this equation to make it easier so that I can get to something I know to do with the antiderivative?